Okay, well, welcome to the PowerPoint slides of Organic Chemistry by Wade. These are taken directly from the book, and what we'll do is start directly in Chapter 1 and get going here. Organic Chemistry. Remember, organic has the word organ in it, so it means that it's the chemistry of life. Organic molecules, you can see these monsters here. There's penicillin, there's Taxol, and here we have codeine. You can see these things look like monsters, but the key thing I want you to focus in on is that organic molecules have carbon atoms in them. So organic molecules are carbon-based chemistry. The chemistry of life is carbon-based chemistry. It can have other atoms in there like nitrogen and oxygen and sulfur and even others. Here, this one here is a sodium salt, so they can even be salts. But the key characteristic is that they are carbon-based. And along with carbon, we will also see always lots of hydrogen in these molecules. We will address more simpler ones than these to get started, so no need to worry. Okay, so kind of a review of the electronic structure of the atom. Remember, the atom here has an inner core that we call the nucleus, and remember that in this inner core of the nucleus are neutrons and protons. Remember that the neutrons are neutral, and these are what gives the mass of the molecule. Remember, the protons are about the same weight as electrons. And outside of the nucleus is where electrons reside. They can reside very close to the nucleus or get further and further out. What this curve is showing is that the electron density is highest as we get closest to the nucleus, and then the electron density tapers off as we get further away from the nucleus, and it tapers off in an exponential manner. In the looking at the p orbitals, remember that these p orbitals are in the second shell, so we'll start by looking at the two p orbitals. The 2p orbital, remember, as all p orbitals, they look like this dumbbell shape. And so in this dumbbell shape, we can look at it with the electron cloud picture, or a picture that maybe we're more familiar with, this one here. Remember that in looking at the p orbital, it has two different phases. You can have a plus phase on one and a minus phase on the other. Remember, those phases tell you how the electron is moving in the wave-like motion, so that this is out of phase with this one. So where these two intersect, we have a node, and so we get this nodal plane here. And in the middle too is where the nucleus is. The other thing to keep track of is the p orbitals, how they can be oriented. They can be oriented in the x, y, and z manner. So there are three ways to orient the p orbitals, and so this will give us three energy slots when we look later at electron configurations for the p orbital. Isotopes. Okay. Atoms tend to have isotopes. Remember, the definition of isotopes is that they have the same number of protons but a different number of neutrons. And so what's going to differ is the atomic mass number. So carbon-14 will have two more neutrons than carbon-12. There's also another isotope for carbon, and that is carbon-13. This is a very important one for NMR that we'll see in Organic Chemistry Part 2. But the key thing is that the mass number, being the sum of protons and neutrons, that's what differs in the isotopes. Now we're going to start getting into electron configurations of atoms. One of the key features to remember when we start this is what valence electrons are. Valence electrons are the outermost shell electrons, okay? And so valence electrons can always be found very easily by the group number, okay? So the group number will give you what your valence electrons are. For example, if you look at carbon, our favorite atom, it is found in group 4, and so it will have 4 valence electrons, which are found right here in the 2s and the 2p. That's the outer shell, and so those add up to 4. And you can do the same thing for the other atoms here. In drawing the electron configurations, okay, we have these different shells. You have the first shell, and then you have the second shell. In the second shell, we have the 2s and the 2p orbitals. What we want to learn is how to fill these atomic orbitals. The first rule we use is the off-ball principle, which states that we put electrons into the lowest energy first, and then we start building up to the higher energy. We then use Hund's rule when we come to the orbitals that have multiple ones in the same energy state, which are called degenerate orbitals. And what Hund's rule says is that I put one electron in each orbital, and then I go back and start pairing up if I have enough electrons to do that. In ionic bonding, remember there are two ways that atoms generally bond. One was ionic bonding, the other is covalent bonding. In ionic bonding, what you're looking at is a cation and an anion getting close enough to have this electrostatic attraction. In covalent bonding, what you have is not an electrostatic attraction, but the thing of electrons being shared between atoms. And there are two types of covalent bonds, a nonpolar and a polar covalent bond. In the nonpolar covalent bond, we have two atoms that are generally the same, and so their electronegativities are the same, and so we call this a nonpolar bond. For a polar bond, what we have are two atoms that are different, and they are covalently bonded together. And so chlorine here has a higher electronegativity that we'll be talking about shortly, and so it will take the bonding electrons and move them closer to it, and we'll see the ramifications of that shortly. It will build up a partial negative charge and leave carbon deficient, and so with a partial positive charge. In Lewis structures, we covered this in our lecture video, so we won't go through these again, but note the different Lewis structures that are drawn for these molecules. What they did was pair up the single electrons in each of these. Note too that any valence electrons that are left over that were not used in the bonding, we have what were called, remember, lone pair electrons. And we always had to show these lone pair electrons even though they're not used in the bonds. Here we have bonding patterns. Carbon, okay, remember, is in group 4, so it has 4 valence electrons, and so as a result its total number of bonds that it likes to have are 4. You'll never see carbon bonded to 5 or 6 things. Nitrogen has 5 valence electrons, but the number of bonds it likes to form is 3 to be neutral, and so it'll have 1 lone pair left over. Oxygen likes to bond to two things, and so it will have a total of 2 lone pair left over in the neutral state. And the halogens like to bond just to one thing, and so they will have 3 lone pair electrons left over. So our non-bonding electrons are typically simply called lone pair electrons. Okay, and these again are valence shell electrons that were not used in the bonds. They were not shared between atoms. You can also have multiple bonds, such as a double bond or a triple bond in molecules. Okay. Talking about the dipole moment, very important. So again, when you have an atom that is more electronegative than another atom, we draw this dipole moment, which is this arrow that points always toward the more electronegative atom. And as a result, a partial negative charge builds up. That's what this delta minus is. And a partial positive charge builds up on the less electronegative atom. Here's just a simple chart of the electronegativity values. We always want to remember that fluorine is the most electronegative atom, and as we head diagonally toward the metals here, we get less electronegative. You don't need to remember all these values, but simply remember as we get closer to fluorine, we get a more electronegative atom. Note that the next most electronegative is the oxygen, and then the chlorine. One other thing to notice is that hydrogen has basically the same electronegativity as carbon, and so carbon-hydrogen bonds are considered to be nonpolar. So never draw any dipole moments between hydrogen and carbon. Here is the concept of the formal charge. In our lecture video, we did a different way than this calculation formula, so we won't go over that, but you should, at this point from watching the video, be able to calculate the formal charge on that oxygen in a more simpler manner. Here, just some more solved problems. Let's move on to, again, the bonding patterns with atoms. Okay, so this is a group 3, a group 4, a group 5, 6, and the halogens group 7. Okay, so carbon, again, wants to have 4 bonds. Okay, if I go less than 4 bonds, it will build up a positive charge. If I put a lone pair instead of that bond, it builds up this negative charge. Okay. Note nitrogen wants to have 3 bonds. Okay. When I force 4 bonds, it will have a positive, and 2 lone pairs will give it a negative. Okay. Oxygen wants to have 2 bonds. When I force it to have 3, it will build up a formal charge, a plus. When I put 3 lone pairs on it, it will build up a negative charge on it. Resonance, we will not cover resonance in organic part 1 because it's not really used until organic part 2. So we'll just go ahead and skip these slides. Okay, just continue to skip these things that I'm sure you will not mind for right now. Okay, just continue to skip these things. Alright, well, we won't skip this one. Here, the condensed structural formulas. Okay, here is a Lewis structure. Remember, the definition of a Lewis structure is where I show all the bonds in any lone pair the molecule might have. When I condense it, I condense all of the carbon-hydrogen bonds, and so show them like this. Note that the hydrogens are written to the right of their attached carbon atom. Okay? So we draw it like this, not like that. Okay, here's some more Lewis structures. So if I condense all the carbon-hydrogen bonds, we get this structure. If I condense all the bonds here, carbon and hydrogen, we get this. Okay, note if I have a bond to a non-hydrogen atom like oxygen, I've got to show that. Okay, and here's the OH that was on this carbon over here. So here's some more condensed structures. Okay, note here we use parentheses. Okay, so this CH has 3 CH3s on it. Okay, and so we put those 3 CH3s in parentheses to show that. Here, this molecule is condensing to 4 CH2s that are right here. So we put those in parentheses to show they are repeated 4 times. Here's some more Lewis structures that are condensed. Okay, note this oxygen has 2 of these on here, so we could even put those in parentheses like that. Okay, this middle CH here has the OH on it, as well as 2 CH3s. Same thing with this nitrogen, NH. It has 2 CH3s on it, so we can abbreviate like that. Okay, here's some more structures, okay, where they are condensing even more. Okay, and here's the important topic of line angle drawings, or what we call line bond structures from the video. Okay, and here remember how we did that. Each carbon atom is represented in the skeleton here, so each mountaintop or valley is a carbon, as well as the end of each line. Okay, and remember that the hydrogens are always assumed. So this carbon here is bonded to 2 carbons, and so I have 2 leftover bonds, which I know must be to hydrogen atoms. Okay, so hydrogen atoms to carbon are not shown. Okay, but when I have other atoms such as nitrogen, oxygen, and halogens, they must be shown. Here's an example. Okay, I have this C double bond O, so the appropriate way to draw that is right here, where I still need to show that to the reader. Okay, also double and triple bonds must be shown, like we did here. Here are some more complicated ones. Okay, so note a carbon-carbon double bond needs to be shown. An OH must be shown if it's in the molecule. Okay, here's nitrogen. Here are some ring structures, so you should be able to calculate how many hydrogens are on each of these carbon in the ring. Remember, always subtract from 4 because carbon is tetravalent. Okay, empirical formula stuff. Okay, this is back from general chemistry. It's not really needed here, so we'll just skip over this here. Now let's look at acid-base theory. Okay, the Arrhenius Acids. Okay, they were simply defined as something that dissociates in water to give the H3O+. That's called the hydronium ion. So here sulfuric acid is giving one of its hydrogens to water to form H3O+. Okay? We'll typically call hydrogen a proton when we deal with acid-base chemistry. Okay? So we want to get used to this word when we talk about hydrogens being transferred. Okay, here with bases, the Arrhenius base is what gives the hydroxide ion. Okay, so these are very common bases as they produce OH- in water. The Bronsted-Lowry definition, very popular definition, even more than the Arrhenius. Okay, acids donate or able to give off protons. Bases are able to accept protons. Okay, so acids like HCl give off its one hydrogen to OH, the base part, to form water. Okay, same thing with sulfuric acid. It gives its one hydrogen to ammonia, NH3, to form the ammonium ion. Okay, here the hydrogen can be given to a carbon of a double bond. We'll see this later on in double bond chemistry. Okay, and here this hydrogen can be taken by this lone pair on the nitrogen. Okay, the key thing here is that these bases must have lone pair electrons. That's what defines a base. Okay, remember the conjugate acid-base theory? So here sulfuric acid starts as the acid, so when it loses its proton to water, it forms the conjugate base. And water, which was the base, forms the conjugate acid. Okay, so you should be able to draw conjugate acids and conjugate bases between any two acid-base set. Okay, so here we're going to look at the effect of electronegativity on acid strength. Okay, so that's what pKa is. It's a measure of the acid strength. The lower the pKa, the stronger the acid. Okay, so here down here, when we look at these acids like HF and water and so on, what we always do is we look at the conjugate base. So remember, I remove a proton to look at the conjugate base, and so I get F minus, OH minus, and so on. Well, the F minus turns out to be more stable because it's more electronegative and is able to stabilize those electrons better. And here's an important principle: the more stable that conjugate base is, the weaker it is as a base. Okay, so weak bases like F minus is a very stable base, and its acid, its conjugate acid, would be much stronger than these others. Okay, so OH minus is a stronger base than F minus, NH2 minus is a stronger base than those two, and CH3 minus would be a much stronger base than those, and as a result it would be much less stable. Here's the size of the conjugate base. So here are the acids that we want to look at. If you look at their conjugate bases, I minus forms is a very big conjugate base, and the bigger it is, the better it's able to stabilize the extra electron. Okay, so it'll have a more stable negative charge. And so this would be a weaker base than any of the rest, and since it's a weaker base, its conjugate acid will be stronger. Okay, so the larger size stabilizes the anion. Okay, again, since we skipped resonance, we'll go ahead and skip this slide. Lewis acids and bases. Okay, Lewis base is again something that has a lone pair of electrons. Here's the Lewis base. Okay, with its available electrons. Lewis acids are electron deprived, and so these are going to accept electrons. Okay, and since Lewis acids can accept electrons, they are electron deprived, and so we call them electrophiles because they would love to have electrons. So we'll be using electrophile and Lewis acids a lot synonymously. Okay, a nucleophile is often identified with a base because it's able to donate electrons, okay, to a nucleus with an empty orbital. Okay, so what we always find is that nucleophiles always tend to react with electrophiles, since these can accept electrons. Okay. Another thing to notice here, a couple other things, very important. We're going to draw mechanisms, and when we do, we'll be using arrows. Mechanisms always flow from electrons to the electron deficient site, or the electrophile. Okay, so electrons will always flow, use this kind of arrow here, from nucleophile to electrophile. And when a bond breaks, the more electronegative atom always receives the bonding electrons that broke. Okay, so we'll see examples of that as we continue. So here are some nucleophiles and electrophiles reacting. Okay, so here we see the lone pair on this nucleophile reacting with the electron deficient electrophile, and so getting this kind of bond forming. Note down here this nucleophile, as it attacks this electron deficient site, remember it's delta plus, the bonding electrons are going with the more electronegative atom, and so chlorine is able to leave as Cl minus.